All right, let's go and take your homework handouts out. The first handout, of course, was the classwork handout that we didn't quite finish. So we're going to start with that here in just a moment. But before we get to the handout, let's review some terms that we talked about. We had a weekend to study. Hopefully you did some studying over the weekend. Okay, good, some nods. I was about to say, I let you have a pre-cal homework so you could study for this. So hopefully you didn't let me down there. Talking about what type of motion here in this chapter, Michael? Rotary motion primarily, right? In general, angular motion, right? So if there's rotary motion, for instance, Michael starts randomly spinning around. Thank you, Michael. He's spinning around in his stool. His feet are in circular motion. His body is in rotary motion, right? So technically angular motion, because we're going to kind of see a bit of each of those, but primarily rotary motion. And the key word to thinking rotary motion, class, is the word spin. With circular motion, we might think of the word orbit, right? Circular motion is an orbit, if you will. Rotary motion is a spin. And with rotary motion, obviously, all of our quantities change. So everything that we talked about with mechanics and movement earlier in the school year last semester, we're not getting rid of these concepts like speed and acceleration or velocity, acceleration, and displacement. We're just changing all of them to angular quantities. So an object, rather than moving from point A to point B, rotates from position A to position B. And we call that amount of rotation, class, angular displacement. Good. But since angular displacement is literally a rotation or an angle, we represent angular displacement with the symbol for angle. Theta rad. And the rad here is reminding us that the rotation has to be measured in radians, correct? And so radians, well, what if I had degrees for the rotation? What would I need to do to go from degrees to radians? Pi over 180. Admittedly, we haven't actually done this too much. Because usually objects that are spinning so fast, or the objects we would encounter in a physics world are spinning so much that we're actually talking in terms of whole revolutions that we have to convert to radians. This one admittedly has come up more often. How do we go from revolutions to radians? Multiply by 2 pi. Of course, to go the other direction, we would divide or multiply by the reciprocal in each case. So that's our angular displacement. Well, obviously, an object could rotate slowly, or not, it could rotate quickly, right? Michael, for instance, was spinning very slowly because it's hard to spin around quickly when sitting on a stool, okay? But the spin rate, as we might call it, is called angular velocity, the speed or velocity at which it spins. Angular velocity, represented by the Greek letter omega. And omega is measured in what unit?
Per second.
Per second, or radians per second. How do we find omega? What is the equation for omega then? Theta rad over t. Not displacement per unit time, but angular displacement. How much did it spin divided by how much time did it take to do that spin? Right, so not d over t, but theta rad over t. And of course, we can even use this to find theta rad in some cases if we multiply omega times t. And we said an object could be spinning at one rate and then suddenly start speeding up and spinning faster and faster, or maybe start slowing down a little bit. We're going to be looking at this a little bit more in a couple more lessons. But the change in angular velocity per unit time is called acceleration, or specifically in this case, angular acceleration, represented by the Greek letter alpha. So a lot of Greek here. And we said that, practically speaking, we could find alpha, angular acceleration, by simply using the formula omega sub f
minus omega sub f.
Good. There's the change in angular velocity. Of course, angular acceleration is going to be measured in what units? The radians per second squared, or just per second squared. And we could use this to solve for alpha. We could alternate solve for time. We could get the omega sub f by itself. In some rare instances, maybe the omega sub I by itself. So we have these equations here. We had another equation that we could use to find the angular displacement while an object is accelerating. Volunteer for that equation. Audrey.
Omega sub I times t plus 1/2 alpha. alpha t squared.
Excellent job, good. And then Michael, the other equation we had involved an omega sub f squared.
Yes, that omega sub f squared equals omega sub I squared plus 2 alpha theta.
There we go. And I always think 2AD, and then I'm like, no, that's right. That's old alpha theta rad. So it takes a moment on that one. Obviously, Kendall, we are praying for you and your family, Nathan specifically. Hopefully, you studied a little bit over the weekend. I know things were a little hectic for you. You're studying over this. Be ready. Hopefully tomorrow you're able to come back and join us. So we'll do our best to review for your benefit as well. By the way, if you happen to not have your physics handouts with you, you wanted to follow along, go back to the previous lesson, Kendall. You'll see those handouts. You can follow along with us here in just a moment. We also talked about the fact that while an object is spinning, for a second object to be on the spinning object, obviously the second object would be in circular motion, not rotary, there has to be a certain force that keeps it moving in that circle, right? Maybe it's an adhesive force of gum stuck to something that's spinning, or perhaps friction of you standing on the spinning whatever it is, right? The force that keeps an object moving in a circle, though, just as we talked about in chapter 11, is still called centripetal force, right? And so to find centripetal force or centripetal acceleration, we had a couple of equations that we doctored up equating some different variables. Do you remember the modified form of centripetal acceleration? R omega squared. And since force is mass times acceleration, centripetal force is?
mR omega.
Mr. Omega squared. All right. Anyway, now these were obtained by finding linear values. Since force and acceleration, these are linear quantities. And we said if I know angular and I want linear, I simply multiply by the radius. So if I want the linear velocity, I'll take the angular velocity times the radius. If I want the linear acceleration, I'll take the angular acceleration times the radius. If I want the linear displacement, which usually we call arc length, I'll take the angular displacement and multiply by the radius. Right? So we don't necessarily have to memorize these three. Just remember that linear equals angular times radius. Good. I think that pretty much sums up, I was on the wrong page, pretty much sums up what we've been talking about here recently. Making sure we got everything there. Yes. All right, so let's take a look at the handout. Again, this is the classwork handout that we started with. We've done the first three problems. We were working on the fourth one. We had a cyclist using a bicycle odometer. Remember, that's a little sensor that goes on the wheel. You tell the sensor how big your wheels are. It does all the math for you. It just texts how many times does the wheel spin. And based on how many times the wheel spins or how fast the wheel is spinning, it does all the conversions into the linear for you. This particular wheel, remember, was 24 inches in diameter. That is, it had a radius of 1 foot, which was a nice, easy number we liked very much. We said it made 1 revolution every 0.183 seconds. But of course, we replaced the revolution with 2 pi radians. And so we said then that the omega, the angular spin rate, came out to is about 34.3 blah, blah, blah radians per second. Well, if that's the linear or angular velocity, the linear velocity back in problem 2 was going to be angular times radius. So it would be 34.3 blah, blah, blah feet per second. Then we said that the cyclist maintains that speed for a time of 10 minutes. So in the third box, we said calculate his linear displacement. Well, remember, I said you can solve for theta rad by multiplying omega times t. So we took his omega, 34.3 radians per second, and we multiplied by 600 seconds. And we found his angular displacement to be 20,600.6 blah, blah, blah radians. Which means then that number 2 is linear displacement is 20,600.6 blah, blah, blah feet. Because linear displacement or arc length, whichever one you want to call it, in this case we're talking about a linear distance because the arc is going to be spread out along the roadway. That distance or arc length is 20,600.6 feet. We're just multiplying the angular times the radius. That's where we left off. Coming to the last box, go ahead and read that final box for us, Michael.
Using the information from problem 2, suppose the cyclist pedals hard for 4.5 seconds and increases his angular velocity to 1 revolution every 0.176 seconds. Determine his angular acceleration, his linear acceleration, and his angular displacement during the 4.5 seconds.
All right, so let me erase these as well. So we're now saying that this was the cyclist's speed. Let's slide this that way. Okay, so this was the cyclist's speed, or linear, or angular speed rather, but then the cyclist pedals hard and he gets up to 1 revolution, or 2 pi radians, every 0.176 seconds. So that means he's going to have a new or final angular velocity, and that wasn't what they asked, but we had to find that anyway. And so what do we get for the new angular velocity?
35.69.
Blah, 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 radians per second. At some point, you needed to find that value. Audrey has it. Michael, do you have that? Okay, maybe you found it and didn't write it down. I'm going to go ahead and write it here. In fact, I'm going to wish I had this in the memory. I'm going to put this in the memory. Actually, I'm going to put it store 2. I'm going to check memory 1. It's not the right number. Okay, so I'm going to go back and put this. This is in memory 2. I'm going to recalculate this real quick. 2 times pi divided by 0.183. And I'm going to put this in memory 1. So I've got both numbers, store 1. Okay, so recall 1, there's that one. Recall 2, there's that one. All right. And it says that it took how long to get to this point? How much time required to get here? Michael?
It took him 4.5 seconds.
So for 4.5 seconds, he increases how hard he's pedaling, how fast he's pedaling, to get the spin rate of the wheels, if you will, up to that rate. If this is how much time it took to go from one velocity to the next, we can use all of that to find, number 1, his angular acceleration. And again, what equation do I need for this, Michael?
WF.
Omega sub f?
Yeah, that minus omega sub I over 2.
There we go. So I can take the memory 2 minus the memory 1 and simply divide by the 4.5 seconds, and that will give me what angular acceleration?
0.303.
0.3034, blah, 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 radians per second squared, remember. Sig figs, I think we're stuck on 2 sig figs, yes? So approximately 0.30 radians per second squared. Did we have that for our first answer? Audrey, yes. Michael, no. Michael, question. All right, part 2 asks for the linear acceleration. Well, class, if you want the linear, angular times radius. So the angular's on my calculator right now. I'm actually going to want this in memory 3 coming up here in just a second. So I'm going to store 3 before I clear it off. I'm going to take that angular and, wait a second, times radius. What's the radius?
12.
Ooh. Well, you could say 12 inches, but I'd rather say 1 foot. Because we want feet per second squared for our acceleration, right? Not inches per second squared anyway. And if you multiply by 1, 0.30 feet per second squared. It's really easy. You're just multiplying by 1. So take whatever you had times 1, but put feet instead of radians. Questions on that correlation here? Again, it works out great when the radius is 1 of anything. Questions? Now part 3. While he was pedaling harder, what was the angular displacement during that time? What's the equation I need for angular displacement during an acceleration? Michael?
Theta rad equals omega sub I t plus 1/2 alpha t squared.
Obviously the t is the 4.5. Here it's going to be squared. The alpha is my memory 3, and that's why I said let's put it in the memory. The omega sub I is the memory 1, the 34.3, blah, blah, blah. So, if you didn't have this answer earlier, Michael, go ahead and recalculate. Audrey, if you say, I think I used the correct equation, you can sit there while he recalculates and while I calculate. Times 4.5 squared. Using parentheses is helpful. Yeah, that's whatever the answer you get. All right. And what do we get for the theta rad, Audrey?
163.7. No.
I think you used the omega f instead of the omega I. That would make you that tiny bit bigger.
Yeah.
Yep, that would do it. That would give it to you. Oh, okay, so close. Michael, do you have it?
I have 154.
Oh, you're wrong. Wrong. Too small. She was too big. You were too small. And I'm not sure how you would have gotten that. Did you figure out what you did?
Yeah.
Should have 157.577, blah, blah, blah. It rounds to 160, so Audrey, rounded to sig figs, it actually comes out the same. 160 radians of displacement during the 4.5 seconds, but 157.577, you have it now. And then Michael, all right.
I forgot to multiply by time squared. I just squared the memory thing.
Oh, okay, gotcha. All right.
Strange. It was right next to it.
All right. Questions on this handout? All right, let's go to the next handout then, which was was supposed to be the homework all along. Go ahead and read the first box for us, if you would, Audrey.
A boy rides on a merry-go-round that, once it is up to speed, makes one revolution every 6.50 seconds. Find his angular velocity in radians per second. You want me to read the second part?
Let's just stop there with the first part. All right, so the first number we need to write down is?
One revolution every 6.5 seconds.
And since it's every or per 6.5 seconds, I'll write it as a fraction, but I'm not going to actually keep the one revolution because we never do. We always make a revolution class into 2 pi. So then it's 2 pi radians if we wanted to write radians. We don't necessarily have to. And I don't have this answer here. So what do we get for the angular velocity?
0.966.
Okay. And I'm going to go and put this into memory because I've got a feeling I'm going to need it. Did you get the 0.966 for his angular velocity in radians per second? All right, questions on how to do that. All right, sig figs, it is 3 sig figs. So that's a 0.9666, thankful for the 9. So we'll say approximately 0.967 radians per second for our first answer there. All right, store 1. I'm going to clear my old memories. All right, then Michael, the second part says,
assume the merry-go-round started from rest before reaching the speed 7.5 seconds later. Find the boy's angular acceleration.
Ah, okay. So Michael, it reaches this speed. So this omega specifically, we would say is the omega sub f. The omega sub I then would have been 0 radians per second. The time it took to change from sitting still to rotating at that speed only was
7.5.
That's not shabby. That thing's actually accelerating pretty decently. So it says find the boy's angular acceleration. Well, by now we should have the angular acceleration formula down pretty well, class. He did it again. I was like, this time he's going to say omega. Nope.
Omega sub f minus omega sub I equals 14.
And Audrey's like, I'm just going to sit there and let him do it because I mean like that. All right. So plug in the numbers. What do we get for the accelerator? Oh, that's actually not that much.
0.129.
Okay, I assumed it would be greater than it was. 0.12888 or rounded 0.129
radians per second.
All right. Now, if you missed part 1, you're doomed to miss part 2. So obviously, we didn't get part 2. Audrey, did you get part 2?
I did not because for some reason I divided the first one by time and to get a different number, and then I divided that one by the 7.5. So I divided by time twice.
Oh, that's unfortunate.
Yeah.
So you had a like 0.01 something.
Mm-hmm.
Oh, that's unfortunate. All right. Questions on it? All right. And then going to the next part. Going to the third part, Audrey.
From the previous slide, the merry-go-round measures 2.7 meters across, and the boy rides at the edge. Find his linear velocity.
All right. Ooh, number 3 says a linear velocity. How do I find linear, class?
Radius times alpha.
Radius times angular, right? Now, A would be r times alpha, V would be r omega. Basically, just find the angular velocity, multiply by the radius. Well, what is the radius?
1.35.
1.35 meters. 2.7 meters across means a radius is 1.35. So we'll take the memory value times 1.35. And how fast is boy going?
0.174. No.
0.130.
The memory value should be a 0.9666 times 1.35.
1.30.
1.30 for blah, blah, blah. Now, how many sig figs am I allowed?
2.
2, because the 2.7 was used to get the 1.35. So we're going to say 1.3
meters per second.
meters per second. There we go. Now again, you could have gotten 3 correct without 2 correct. Right? As long as you had 1 correct, we could have gotten 3. Did we get 3 correct? Okay, question. Michael, question.
I didn't have 1 correct.
Well, I knew you didn't have 1 correct, so I knew you were doomed. That's why I didn't ask you if you got it. I just said questions. All right. And then number 4 says that the boy weighs 325 newtons. So what, about a 75-pound kid? Find the centripetal force acting on it. I've got 2 different equations I could use for centripetal force. Give me one of them, Audrey.
M times r omega squared.
Good. Mr. Omega squared is our new one. Do you remember the old one, Michael? Centripetal force equation?
No.
mv squared over r. If we happen to have the v still in the calculator, this is helpful. I happen to have this in the memory still, though, so I don't know that I need the mv squared over r, because I've got the mr omega squared. Omega's in the memory, r is 1.35, but they don't give us mass, they give us weight. So I'm going to use this to find the mass.
33.16.
Good, it comes to 33.163, blah, blah, blah. Mass measured in kilograms, remember. So I'm going to take that value, still on my calculator, times the 1.35, times the recall 1 squared, to get how much force holds the boy on the merry-go-round.
41.7.
I think you might have used a rounded, but I got 41.833, blah, blah, blah. But we're still using, because again, the radius came from a 2 sig fig number. I'm still using just 2 sig figs. We would both end up rounding to 42 newtons of centripetal force. 42 newtons. All right, sir. Questions on this? Any questions at all on what we've talked about in section 13.1, Introduction to Rotary Motion? All right. Clear desk except for a clean sheet of paper, pencil, and a calculator. Clear desk except for a clean sheet of paper, pencil, calculator. Everything else away. First last name at the top of your paper, along with today's date, which is 1/9/23. Today is the date of the College Football National Championship. I'm rocking the TCU colors because I hate Georgia. It's not my most hated team, but you know, there's enough obnoxious Georgia fans around here. Go little guy. I mean, TCU, with its 5,000 students, beat University of Georgia with its 60,000 students. So anyway, 1/9/23 today's date. Go Frogs. Horned frogs. It's more important. All right, and this is quiz 16. Quiz 16. Let's go and take a look at the quiz together very quickly. First section, you got short answer, fill in the blanks, or answer the questions as needed. And then the problem solving. You'll notice that everything builds on the information in a given and in number 7. So using all of that to solve the problem. I'll go and write the homework on the board. For now, go and begin your quiz, and I'll end the video with the homework on the board.